Welcome to another video explaining the universe using the particle model. My name is Bob Hilster and I am your particle model guru. Today's video is a continuation of the review of my book, Gravity is Not Free, Part 4, in particular, about R squared, which I claim is not a law. Gravity is Not Free is the title of my book, and it covers the period from the early 1990s to the spring of 2015. However, I do cover light, and the light part goes beyond the time frame of my book. But there are these parts of my book. I covered part 1, Dave, and parts of part 2 for Bob. I'm not covering part 3. And this is the second video covering one of the papers in that part 4 section. I covered the 3 main objections, and today is R squared. So let's look up R squared in Wikipedia and see what it says. The inverse square law in physics is any physical law stating that a specified physical quantity or intensity is inversely proportional to the square of the distance from the source of that physical quantity. The fundamental cause for this could be understood as geometric dilution, and we'll get into that. Fundamental cause is geometric dilation. That's the cause. It does. There's a lot of geometry involved, and it corresponds to a point source radiating into three-dimensional space. What got me, they were also saying is a physical law, so I wanted to find out what that was, and so I looked it up and continued on here. Scientific laws or laws of science are statements based on repeated experiments or observations. Stop there for a moment. It doesn't say theory here. It says experiments and observations. When you have a law, physical law, stated in words or equation, and is based on a theory, it's really much stronger in its implication of what's there, because there's some substance behind it. When you base the equation or words on repeated experiments and observation, that's called an empirical equation, and has generally no theory behind it. But here's the next point that's interesting. The term law has diverse usage in many cases. Sometimes it's approximate. A law is approximate. Accurate? Yeah, that's what we thought. Everybody thinks laws are accurate. Broad? Yeah, okay, can cover many areas of science. Or narrow, meaning maybe only one area of science. Broad or narrow, accurate, approximate? No, that's not the way people understand it. Many people, including scientists, consider a law to be exact, true, and must be accepted, used without questioning its validity. Many scientists go forward. They use R squared as a inverse square law in determining dark matter, and they use G as a universal constant. You can't change it. That's what it is. I heard, and I've said this before, I heard a gentleman give a talk on a teleconference where he said light obeys wave theory. Well, in this case, at least he's talking about a theory, but obeys. What does light have to do? Walk up and read the theory so it knows what to do? No, light does not obey anything. It does what it does. So where is R squared used? Well, it's used in a lot of places. Gravity, there's R squared. Electrostatics, Coulomb's law, R squared. Light, intensity is proportional to R 1 over r squared. Sound intensity is, again, pressure over r squared. And r squared is used in general in any point-to-point calculation. One of the things that I'm talking about here in terms of r squared is, number one, is it only a matter of distance? And therefore, how accurate is it? Second question is the particle model. This is the equation I derived for the gravity experiment did many years ago. R squared does not appear in that equation. It appears here, and yet this equation worked quite well. So let's take a look at sound. This was the equation I just showed. The intensity is equal to the source pressure at this point, divided by 4 pi r squared. It's inversely proportional to r squared. So here's the point square. You go out r and you've got this much intensity. The amount of intensity that's here is the intensity here. Go out to 2r, and now that same intensity is spread out over 4 areas, 4 times the area, and then 3r, it's 9 times the area. That's the whole point of dilution by distance. That's all r squared is talking about. But in sound, we have, to talk about the physics, we have air molecules. Sound is air molecules pushing each other back and forth. I'll show that a little bit later in the next slide. But the molecules do not, air sound does not, the molecules don't propagate at all. There's an apparent wave that propagates, but the molecules push each other back and forth. What is the force that sustains this oscillation as these particles move back and forth? The answer is really gravity, but to go into a detailed explanation, that's not my point here. My point is, for sound, you have a medium, there's air molecules, they're moving back and forth, they're not propagating forward in space. There has to be something that sustains these oscillations if that's what's happening. And then finally, elastic collisions reduces the intensity. Air molecules are not rock solid. When they get pushed together, the pressure is going to move them back out, and when there's nothing there, the high pressure is going to recollapse. That pressure back and forth, in my opinion, is being caused by gravity. But the elastic collisions that happen in the process loses energy. The amount of momentum that one particle imposes on the other is not transferred 100%. So it's going to lose intensity by that. This equation implies it's only distance. It works well. It's an empirical equation, but it really doesn't get into the physics and describe what's going on. As a consequence, as an engineer, you might use this to say, well, how much light am I going to have at the back of the room? Yeah, you can use a light meter, and it's going to generally follow that rule. But all these things are going on. Okay, this is a great video. You got to watch this. This is the link. I will put this in the description so you can just copy and go there. But when you step back and watch this, you got a speaker generating, vibrating back and forth, generating pressure and creating this ring. And you can sit there and watch that ring as it grows and gets bigger, and it gets here, and then it grows bigger, it gets bigger. So you can see the wave propagating. But the interesting part is if you look at this particle right here and watch it, the only thing it's doing is moving back and forth, back and forth. Same over here. This one's moving up and down, up and down. Same down here. This one moves up and down. Of course, some of them are moving at angles. And yet, when you step back, it looks like the wave is propagating, but those molecules aren't moving. And r squared talks about the intensity here is higher and it's less here and it's less there because of the dilution, but also because of other things. Excuse me. Okay, what about light? Well, this was the equation for light. It's an empirical equation. This is the same diagram. You have a point source, and the amount of energy, intensity, generated here is all there. Now it's spread out over 4, then over 9. Now, I'm not an etherist, but most people assume light has to have a medium, just like sound. Sound has a medium of air. Light has to have a medium. Most of people call it ether. What about space-time? Well, you can get various answers to this that I've seen on the internet where it sure appears that when you hear about space-time fabric, that there's something there, or when you hear that space-time is being bent, how can you bend something that's there? It must be there if you're going to bend it. I'm not an etherist and I'm not a relativist, so I'm not going to be able to explain it, but let's assume that there is light and that light is ether molecules and maybe atoms pushing each other back and forth and propagating just like sound. Biggest question I get is what sustains the oscillation? And I hear a very general, well, there's ether pressure. Yeah, just like gravity, but what is that pressure? Where does it come from? In gravity, the particle model, I claim it comes from these particle models get emitted from all the stars in the universe and are propagating through space. But here's another interesting point. Because light moves at speed c, the ether must be inelastic. If it's elastic, how does it propagate at speed c and get from Andromeda galaxy all the way to us without totally being lost? And if sound doesn't propagate that far, of course, sound doesn't propagate at speed c either. But this empirical equation, which is useful, and as you're going to measure light at the end of the room, that works very well, and it seems to work that way in general. But the physics of ether, or how light propagates based on relativity, I'm guessing. I'm not an expert in that area. But now the particle model of light. This is a diagram I've shown over and over again. And again, light is a stream of G1 particles moving at speed c with a repetitive pattern. They got lots of 4 particles here, almost none here, 4 here, and so on. It's a repetitive pattern. Dave, my son, generated this stream of particles based on a sine wave. He had to, I don't know what he used, but he had to use an equation like this. If you just use the sine value, sine has a plus or minus, which means you're going to have a positive number of particles and a negative number. Well, you can't have a negative number of particles. This formulation guarantees, it shifts the curve up, so to speak, on the graph and guarantees the number calculated is always positive or 0. In the particle model, for the medium, there is no medium. It's just wide open space. If you shrink yourself down to the size of a G1 particle and move through space, it's wide open. There's lots of G1 particles flying around as well, but in terms of the G1 particle, there's wide open space, and they just move in a straight line. What keeps them moving in a straight line? The G2 particle field sustains the particle, gives them G1 as they hit equally left and right, up and down, that moves in a straight line. That's what keeps it moving in a straight line. They don't ever explain why light moves in a straight line. It does. You kind of know that. You don't question it. But the physics of it has to tell you what keeps it there. And I'm saying G2 particle field sustains it. Of course, it sustains the velocity as well with a little bit of drag, as I've mentioned many times. But here's another thing that has to do with the intensity. The G1 particle field, not the G2, can hit the other G1s, and they'll collide and bounce off each other. And you could have a G1 particle come flying through here and knock this guy out, and he's gone. Knock this guy out, and when you knock these out, the amplitude goes down. These guys out. You can knock these guys out here. Probably won't make much difference because the amplitude is determined by the number of particles at the peak. So the intensity can be reduced by other factors. But even so, a light meter can be used to measure the light in a room. Well, what about gravity? And here's Newton's equation for gravity, and this has got the gravitational equation in here, and there it is again, r squared. What's the medium? Newton has no theory, no medium, but he was able to generate this. He used three other equations, which are empirical equations from Kepler and so on, and his own equation, F equals ma, to generate this. It's made from observations and measurements, no theory. But the r squared law is based on this geometric dilution because the amount of strength of this source is diluted as it moves out by the inverse square. And basically gravity is point-to-point mass. I'll go into that here. But I'm going to back up, and this is now my equation, and the equation doesn't say r squared. R squared does not appear, and yet the equation works. This specific equation was developed to calculate the force of G1 particles as G1 particles come at this object. And the point of interest, there is a point of interest, the ball, right here, the center of this ball is the point of interest. And what I do is, with this double summation, that's what makes it three-dimensional, but let's just look at one dimension, the horizontal plane. You look at this plane, this sheet is like a horizontal, the floor is like a horizontal plane. You got an angle 0, 1, 2, 3, 4, you go all the way around 360 degrees. Some of the paths do not go through the lead bricks. These do not go through. Others go through, and if you calculate the number that's there and the number lost depends on the amount of mass that goes through here and here, and this way. So this is not point to point. There is a point of interest, but the calculation is three-dimensional and takes in the whole geometry of the system. It's not a question of this point to this point, and you can do it that way. Kind of did it that way to compare to what Newton did. R squared appears because of the system geometry, because of the double summation. But I wanted to kind of prove it mathematically. I wanted to find the r squared mathematically, and I used this diagram to do it. And here's the Earth, and there's a point on the surface. Then that's one dimension of 1r, then 2r, then 4r, then 8r. And I did a calculation, and what I assumed was that 1 over r squared is proportional to the ratio of the total number of paths to the number of paths that pass through the Earth, or the number that are reduced versus the number. See, out here, all of these paths out here, this way and this way are not reduced, but the paths that go here in that green area space, they're reduced by the amount that they're just reduced by the amount of mass is what I was trying to say, but I didn't include mass in this calculation. This is what I got. I did a 3D calculation. I remember I did it on a spreadsheet, but I couldn't find it. And I did not include the mass, and I claimed that if I had done it properly using the C++ program, which would take me time at the time, decided not to do it that way. But here's the distance r, 1, 2, 4, 8, I even went to 16. R squared is just r squared up to 256. The ratio is taking this value divided by that is 4. This value divided by 4 is 4, and so on. And geometrically, in a precise sense, you get this 1 over r squared. When you double you get a ratio of 4. When I did the three-dimensional calculations, this is the total number of particles that are going to pass through the point of interest, and this is the number that are reduced. And these are the numbers I got. So if you take this number, divide it by 90, you get 435, and then 411, 409. And if I remember right, when I got to 16, it didn't look right again. To me, that should have gotten smaller. But again, I'm using spreadsheet, and it probably, my conclusion at the time was that the spreadsheet wasn't accurate enough to give me a good answer. Still, very, very close. It shows that the geometry of the system is very close. And by the way, Melbourne Gene Evans wrote this paper on Newton's equation and r squared and his ideas of theory, and he wrote it in 1958. And in it, Newton talks about r squared, and he states, or Melbourne apparently quotes Newton as stating, that he was pretty sure, pretty confident that r squared was valid out at long distances. And you can see that if I done this accurately, you got at the further and further away you get, the closer and closer you get to r squared. But that he was unsure that it worked on the surface of the earth in particular, he stated. With the tree, the apple, and the earth, he didn't see how his equation and how r squared could really be accurate at that point. And this kind of shows that, yeah, it was valid at long distance. Why was it valid at long distance? Because Kepler's equation that Newton used to develop his equation for gravity were based on the orbits of the planets. Those are large distances. And in that case, r squared probably works quite well. So my conclusion is r squared is not a law. Nature doesn't obey these things. There are other factors to consider. There's generally no theory behind these theoretical equations, these empirical equations. And there are other factors to consider. R squared does not explicitly appear in TPM's gravity equation, but it is implicit in the geometry of the system, and more specifically in the double summation. As you go around and calculate these things, you find there are times when it passes through and does not. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.